Oh, fantastic. Fantastic. Okay. Yeah. So officially we're starting. Thank you very much. So thanks for your patience. So the question is, how do we go from, just thinking in our head that I need to control this process to actually setting all the required parameters? I mean, determining all the required parameters, all the things you need to control, and then the way you have to control them, understand what the control strategies, the appropriate control strategies to employ, deploy all of those things, program them, even determine whether you're going to use just purely a SCADA system or a DCS or a PLC system, whether you're going to use open loop or closed loop control, all of these are decisions that needs to be made, and of course, that there are ways engineers make decisions. So that is the tone we want to set with this morning's lecture, right? And then subsequently, begin to take bits and pieces of it all through the year. So I'll share my screen. Okay, so I'll start from this. This is an article. So I'll just be presenting slides, right? I'm going to host this article somewhere, and I'll share the link onto the WhatsApp group. For people that are new, we have a WhatsApp group where we share information strictly about automation and control systems. So this is a narration of all we'll be discussing, right? Control systems from conception to commissioning, a practical journey from ideas to operations. And it's designed to bridge that gap. Students in the university, or in fact, many of us, when we were in the university, we were taught control systems from the perspective of mathematics, right? Without any bearing to the applications in industry. And then when we got into the industry, we started looking at control systems as hardware and software without paying attention to the underlying theories, right? The mathematics behind it, the algorithms behind it. PID becomes, something that is neither here nor there. Okay, PID is mathematics. We know it as proportional integral derivative, and we hardly go beyond that. We need to evolve into the kind of engineers that will be able to enter into a plant and then tune it. You step in and then you are saving the plant money, because if you are able to tune your control systems properly, you will save energy. The system will work more efficiently, and then the company will see the results reflected in their balance sheets in terms of Naira and Kobo, right? So you'll see this article and then you can read it. It's quite, maybe about 5 pages, right? Read it and all right. So to our subject today, I just have about 17 slides, but I'm sure there will be a lot of discussions and questions, right? I think you can just note your questions and then we'll take it. Or you can drop questions in the chat box and Aurelua will help to monitor that and notify me if there's a question we need to attend to. Excuse me. Okay, so we're going to approach this from using a case study. We're going to use a case study to illustrate our subject today. And what you have on the screen what you have on the screen is a production system, right? Okay, let me go to the next slide. Yeah. Okay, so this is a picture. So what you have on the screen here is a production system. You can see um, the oil well, right? You can see this tank. You can see this pump. Essentially, now this is a continuous control example, but all control systems projects evolve exactly along this line, right? We see this kind of processes mainly in the oil and gas and what we call the process industry. In manufacturing, we look at batch processing a lot more, right? But the concepts are the same and will be shifting between the two sectors, the process and the batch industries, right? So the concept here is that this oil well, right? This is the earth crust, right? And there is oil stored in what we call reservoirs, right? So there is oil, and then this oil flows through this reservoir. This oil goes through from the earth crust, then comes through this wellhead. Sometimes we call this wellhead a Christmas tree. And then it flows through a pipeline, right, into this tank, right? When this crude exists as a mixture of oil, the oil we need, water, gas, then all of this plus sand, of course, it's coming from the earth crust. So you essentially have four components flowing from the reservoir into this tank, right? And then we'll explain all the instrumentations we are looking at. I mean, all the symbols, So the function of this tank, right, we call it a separator tank. The function of this tank is to separate oil, right? We then pass this oil. We either sell it like that or we send it to the refinery, right, to further process it and break it down into subsequent hydrocarbon components, kerosene, petrol, diesel, and so on, right? And then we separate gas. The gas, depending on the constituents, we can compress it. We can turn it to LNG, liquefied natural gas. We can use it to drive generators. We can use it for cooking and all of those things, depending on the components, right? Then water. So we take this water, we purify it, and then return it back to the environment. We have enough water, so we don't need to store it. So that's essentially what this process is about, right? Let me clean this. I like writing on my slides, but because I'm going to share this, let me clean it so that it will be a bit neat. All right, so that is our case study. So this is an actual picture of an oil well, a Christmas tree. So this pipe extends deep into the earth crust, right? Sometimes hundreds of meters deep into the earth crust, right? And then all of these valves, they have their functions and parameters that will be monitored and all of those things. This is called a choke or something. right? And then this is the pipeline. This is the flow line, that takes this crude into that tank I showed you earlier, right? So the case study context. This case study focus on a single crude oil production system designed to optimize efficiency from extraction to processing. The system routes flow from the wellhead to a central processing facility, terminating at a production separator. The key focus areas include measurements, control, protection, and operability. So the owners of this facility, what they are concerned majorly about is they want to be able to measure. Of course, principally, they want to measure the amount of crude they are producing and other parameters that help them to produce that crude, such as the pressure, the flow, and the temperature, right? They have to measure that. They have to measure everything that has to do with this pipeline. So in this example, this is a subsea pipeline, that is, it is buried underwater. I mean, in other situation, you have the pipeline on land. Wherever the pipeline is, you need to measure, you need to monitor it and ensure that it is in good condition, because this pipeline is carrying hazardous materials, whether on land or in water. If this pipeline ruptures, for example, crude will flow into water and is going to cause environmental pollution. It's going to kill aquatic life. It's going to affect the economics of the host communities. So it is the responsibility of the owners of these plants to ensure that this pipeline is well protected. And of course, a pipeline, it can corrode, it can erode, it can rupture. Even the crude flowing in it can cause what we call hydration, such that if the initial diameter of that pipeline is, let's say, 20 inches, over time, the effective diameter could reduce to 10 inches due to the formation of hydration and other deposits, right? So the owner of this facility needs to measure, needs to control. It needs to control, because what if there is an incident around here? Let's assume that there is fire here. I mean, at the very basic level, if there is fire in this environment, the first thing he wants to do is to be able to cut this supply, so that at least there will be no crude coming into the separator. At least so that the fire will not have any fuel. So that is one of the first things we want to do. So a control system needs to be able to do that. And then it needs to be able to determine in the first instance that fire is there without manning it, without having an individual standing there watching, right? Then it needs to protect. So I just mentioned about protection of the pipeline. Also, this tank needs protection. This wellhead is an economic asset. It needs protection, right? Not necessarily protection from theft, but protection from anything that can stop it from producing in the first instance, and then protection such that it will not constitute an hazard to humans that are operating this process. So measurement, control, protection, and then operability. This system should be easy to operate, right? It should be easy to operate. That's the essence of having it as a control system, right? Okay, I saw a question. Okay, so there's no certificate of attendance. This is purely a tutorial, not a training, right? A paid training will have a certificate of attendance, but this does not have a certificate of attendance. So, in summary, the high-level process flow, you have the wellhead, the entry point for oil extraction begins here. And then you have the pipeline, right? The oil will flow under pressure. So the wellhead, the reservoir is at a very high pressure compared to the ambient pressure. So that is exactly what is pushing that crude outside, right? It is coming out. Okay, can anyone hear me?
Yes, sir, we can hear you clearly, sir.
Okay, so if you can't hear, you need to probably log out and log back in. Or someone please send him a message since he can't hear, so he won't hear the instruction, right? So the wellhead, where you source the oil from, and then you have your flow under pressure, and then you have the separator, where the crude, the crude is what comes from the earth crust, and then it is broken down into its different compositions: water, oil, and gas. And then the sand will stay in the tank. When it gets to a certain level, the sand will now be evacuated, right? So, I mean, this is the tank. You can look at the details. I'm not going to focus more on technical details. I'm focusing more on process today, right? We'll start from subsequent tutorials. We'll start looking at the technical details, and then we'll drill down into all of those, right? Okay. So again, the major equipment, we have the wellhead, we have the pipeline. We have the pipeline, right? That's a typical pipeline on land. And then we have the separation system, separates oil, gas, and water phases efficiently. All right. So now, the instrumentation overview. In order for us to sense, right? In order for us to sense what is happening on the wellhead, we need to put what we call sensors. These sensors are the same things we refer to as instruments, right? So we need instrumentation on the wellhead. We will need instrumentation on the pipeline. We will need instrumentation at the inlet. This is the inlet of the separator. On the separator itself, we will need level and pressure instrumentation and control. And then external to the system, we will need utilities, right? We will need to monitor the temperature, separator temperature, and other utilities. Utilities, for example, what we call instrument air. Instrument air, which is used to drive the valves, right? So we begin to, if you look at the image now, for this system, we need to look at the instruments, we need to look at the separator, the separator instruments, right, we need to consider the outputs, right? We need to determine. So recall, a three-phase liquid enters the separator, and we are having oil and gas, and then water, right? We're going to pass this gas to, whether it is to flare or to a compressor station, right? We're going to pass this oil into some kind of tank for storage or a vessel to take it away, right? So how do we tie all this thinking together? The first thing we do is we define what we call our control philosophy, right? Recall this diagram, the control loop. You have the controller, you have the actuator, and you have the sensor, and then you have the process in between, like that, right? So this is the sensor, this is the controller, and this is the actuator. So you now need to, how do you tie together? So the question is, how do you tie together the monitoring and control requirements for the wellhead, for the pipeline, and for the separator, right? And this is our model of thinking, right? So you need to sense, you need to control, you need to actuate. If this tank is getting too full, you don't want the liquid to spill. So something must be able to tell this tank, something must detect when this tank is getting too full. That is when it gets to a particular level, and something must actuate in order to either evacuate the fluid or stop the flow from the pipeline, right? So the first step in doing that is to determine what your control philosophy will be. Your control philosophy is, a high-level document. We'll still see this down the line, right? This is just to explain the the case study, so that when we get into the process, you'll be able to relate it, right? But the control philosophy is a high-level document that defines how you want to implement your control, right? So it's the first thing you write immediately after your conception. You do your requirements and everything. Is a first document you write, because it could be, so you can see this control philosophy feeds eventually. It fits eventually into how you design your control system, right? What we call your BPCS, right? And then also how you design and implement your safety system, right? Your SIS and safety systems, right? Okay, so the instruments overview. So these are the tags and their function. The PT represents the pressure transmitter, and is to monitor pressure. Let's leave this, right? Let's just say that this PT monitors pressure. The TT is temperature transmitter, and it detects abnormal thermal conditions. The FT, flow transmitter, measure the crude production. The XV, which is the shutdown valve, provides emergency isolation. Emergency isolation between the wellhead, between the pipeline and the separator. And then there is another SDV on the wellhead that provides isolation between the wellhead itself and the pipeline, right? Then we have the PCV. PCV, so PCV and choke are actually two different things, but so we use choke on the wellhead, PCV on the process, right? So, but let's accept it as, for this purpose, treat them as the same. So the choke control valve, it's used to regulate flow. It regulates the amount of crude you release from the Christmas tree or the wellhead. And then the PSL and PSH. PSL is pressure safety low, PSH is pressure safety high. They are essentially pressure switches and they are safety shutdown triggers, right? Because we are focused on the process, there are a lot of thinking that goes behind. So, for example, let me see. Okay, so for example, this wellhead that you have on your screen, sometimes the rated pressure at this level, this place we call it the tubing head pressure. So the rated pressure you see here could be maybe as high as 10,000 psi. 10,000 psi, for people that are not familiar with the scaling of pressure, if you place your palm on 300 psi pressure, it will tear it like paper, right? Or let's say 500 psi, right? As in there is a pressure source of 500 psi and you expose your palm on it, it will scatter, it will tear the flesh, probably just expose just the bones, the cartilage, to tear it like paper. So you can now imagine what 10,000 psi is, right? Now, the fact that this is 10,000 psi does not mean that we're going to operate it at this maximum pressure. But for this purpose, it is 10,000 psi. Now, the pipeline itself could be rated maybe 6,000 psi. And then the tank, let's say maybe the tank is rated at 3,000 psi. What this means is that if you operate this tank, this wellhead at its maximum capacity, it's going to rupture this pipeline. It's going to rupture it. So you need to monitor the pressure that goes into this pipeline such that it will not exceed 6,000 psi. And that is where what we call the PSH comes in. Pressure safety high. So, like we said, it's a pressure switch. Once you set it, maybe you set it at 6,000, or of course you set it at maybe 5,500, a pressure lower than the rated pressure, right? Once it senses that pressure, it switches and then activates the SDV on this wellhead and shuts down so that it does not permit pressure to get on this, high pressure to get on this pipeline. Now, PSL, pressure safety low, right? So the PSL monitors if the pressure on this wellhead becomes lower than the pressure on this pipeline, we still want to shut down this pipeline. Reason is that if this pressure on this side is lower, then there will be a backflow into the wellhead. That is, instead of you producing oil, you are returning oil into the reservoir, which the owners of the plant does not want. So these are the kind of thinking and analysis that you will do, as the control systems engineer, right? Let me just leave this note there. Okay. So pipeline instrumentation, ensuring integrity and safety, right? So on the pipeline, we store instrumentation, FIC, flow indicating controller, FT, flow transmitter, pressure transmitter, and all of those things. Yeah, so for people that are experienced, you will see inconsistencies on this document. Just ignore it. I really worked in creating the prompt to generate the document from AI, right? So like this now, it's meaningless, But I mean, this is serving our purpose in just illustrating what we are discussing, right? So you have your instrumentation, all your instrumentation on the pipeline, right? Again, just for clarification, this is also another kind of oil well, right? The one I showed earlier is called the Christmas tree, right? This one is called the rod pump, right? We don't have this type of oil well in Nigeria, but it's prevalent in the US and in the Middle East, right? So, I mean, just to clarify that. Yeah, let's continue. So then the separator inlet. So the separator inlet control is critical for ensuring optimal operation and safety in oil production. The key instruments include the flow transmitter for mass balance, the pressure transmitter for monitoring the separator pressure, and then the PCV, pressure control valve. If the pressure increases, then there is an action. There has to be a control valve, that takes action, to manage gas outlet pressure. Additionally, there is what we call a PSV, pressure safety valve, that acts as a protective device, preventing overpressure conditions, which is essential for maintaining system integrity and reliability. Right? So all of these requirements, you have derived it from the concept. You have derived it. Thank you. So please, you can switch off your camera, right? So that we are all able to concentrate. Right. So all of this, you have derived it from the concept given to you by the operator. You are the one that will now translate that concept into requirements like this. And then for the separator, so this is similar. This is what you kind of see in the separator, right? So you can see the oil layer, the oil and water interface, and then the water layer. So the separator essentially is working using the principles of physics. Oil and water they will not commingle, right? I mean, they will not mingle. Oil will stay at the top because of its density, and water will be at the bottom. But then you will see this interface, right? You will see this interface. So you can see this dedicated meter for that interface. So we are monitoring that interface. We are monitoring the oil itself, right? And then we are monitoring the overall level of fluid in the tank. So all of these things are what will go into our program, right? And then we write the logic on how everything will interact. Is it making sense so far?
Yes, yes, we are learning a lot. Thank you.
Okay, fantastic.
Yes.
Fantastic, thank you. All right. So, and then we have the temperature and the utilities. We monitor the temperature of the tank so that you have optimal process conditions in the oil production. And essentially, you use a temperature transmitter to do that monitoring, right? Because again, if temperature elevates too much, it can initiate combustion, which causes, that is fire. And you don't want fire in the plant. You don't want to burn the plant down, right? So at the conception stage, when the owner of the plant comes to you as a control system engineer and say, hey, I need to build, I'm working on this project. I just acquired an oil mining license. I want to start producing the oil. The regulator says that I must produce the oil efficiently. I must protect the environment. I must protect people. That is, my health, safety, and environment is critical. Otherwise, they will shut me down. If they shut me down, I will go into debt because my investors will come after me. So I need you to design a control system that will ensure that there is no environmental damage as a result of my operation. I want a control system such that it will not kill my workers. As in, it will not be so dangerous to kill my workers. Also, the regulator said that they want to know to the nearest centiliter or centiliter the amount of crude I am producing from the field. So your control system also must be able to measure the amount of fluid or crude coming from the reservoir. Now, this crude, I want it separated. I want the gas to go to a flare because I don't have money to build a compressor station now. So let's burn off the gas. And then burning off the gas must be done safely, right? I want the crude to go into a tank via a pump, right? And then I want the water. The regulator said that the water must be treated to X purity level and then properly discharged back into the ocean or into the environment. So that's what I have in my head. How are you going to help me? So now you, as a control system engineer, will now sit, you take your pen and paper, you note all these requirements, and then you begin to ask questions. So some of the key questions you ask is, what production rate is desired? Production rate that you desire will determine the sizing of your valves, your pipes, and your vessels, right? So you ask the person the production rate. You ask the person, what are the risks that must be managed? So you tell the person, hey, okay, the person will tell you risk, environmental risk, human risk, economic risk, and all of those things, right? You want to prevent blowout, you want to prevent overpressure, right? And then you ask the person again, what level of automation is required? Do you want total automation? That is, you don't want any human in the loop, or you want some kind of partial automation where machines will do some, humans will do some, right? You know, these days we have what we call cobots. Cobots are robots that work in hand with humans in the plant floor. And these same questions apply in manufacturing. What kind of machine do you want to design? Or what kind of machine do you want to control? Let's say a packaging machine, right? And how many packages do you want to deliver within a minute? So that you use that to calculate what you call your throughput. You know, the same question applies to a conveyor system. How many products do you want this conveyor to deliver per minute? Right? I've worked on a conveyor system in this country that churns out product worth 50 million naira, I think, per hour. Is it per hour or per day? Yeah, I think no. I think per day. That particular line churns out product worth 50 million naira per day. And you, as a control system engineer, excuse me. So you, as the control systems engineer, you need to design that line to be so efficient that it will not fail. Because if it fails, it means that the owner of that plant would have lost 50 million naira every 24 hours that line stays failed. So you can begin to see the level of responsibility that lies on the control systems engineer. So once you ask all of those questions and you do your analysis, you generate a documented process description, and then you generate a very high level control objectives, and then you define the safety intent. This is the key word. You define the intent that this is the direction we are going in safety. This is the intention, right? You've not gotten to the details yet, right? So the key insight here is that your control strategy starts with intent, not instruments, right? Then you move on to the philosophy. So your control philosophy is a document that defines how you are going to implement this control. So maybe you're going to use fail safe. I mean, of course, sorry. In our own industry, safety requires everything to feel safe, to feel safely, right? So the control philosophy defines how you are going to, the kind of mindset you're going to follow in implementing your control. For example, you might say that for this tank, you want, so on this tank, for example, now you have your TT and you have your, okay, so this is not well made, right? On this tank, you have both, you have your PT, you have TT, you have LT. You might decide that on this tank, I want PT to take priority in control. That is, if there is going to be a shutdown, it is going to be initiated by PT, right? So those are the things you determine in your control philosophy, right? So the core control strategies for our case study, right? The wellhead choke valve, the control flow, the pressure control, the PCV, the level control, oil and water controllers, the safety, ESD on high pressure or level. ESD is emergency shutdown. Your alarms, when you want the operator or human to intervene, your interlocks, your automatic shutdown logic, right? And even your permissives, right? Permissives are requirements that must be in place before you start up. So this is just another slide illustrating all those points we listed in the previous slide. So just give me a second, let me take question. All right. So the life cycle is you start from conception, then you move to feed, you move to detailed design, you do your installation. If it's a brownfield, the brownfield is a field that is existing and you're doing some kind of upgrade or whatever, then we call it recommissioning. If it is a green field, we call it commissioning. A green field is a brand new plant you are building from start, not an upgrade, not a modification, right? And then from commissioning, you move to what we call ready for startup, RFSU, and then you hand over to operations. So at this point, the project guys get off the stage, and then the operation guys takes over. From year to year, projects owns all the responsibilities, right? Okay, so the conception phase, like we asked earlier, what production rate is desired, what risk must be managed, blowout, I mean, those are risks. What level of automation is required. The output from this conception is you have your process description, your high-level control objectives, and your intent, right? And from that conception, you know that you need to factor in the production targets, the operability, safety. For example, in this country, some of these wells are on the Atlantic Ocean, and people are not living there. So in order for you to visit this place, you need to fly an helicopter in order to visit this wellhead. You need to factor that in at your conception phase, because this is going to constitute an OPEX, operating expenditure. So how will you design your automation such that you will reduce this OPEX? Right. So these are the kind of thinking that you need to have in mind. You look at your pressure, you look at your temperature, you look at your flow rates. For the pipeline, you look at the pressure, you look at the temperature it must be operated. And then for the tank, for the vessel or separator, you look at the pressure, you look at the temperature, you need to look at the volume. Yes, I'll share the documents. So you look at the volume, right? So those are the questions you ask at the beginning. And then you get to feed stage. Feed is end front end engineering design. And then the activities here, you develop the process flow diagrams. You define the control philosophy. You select major instruments, keyword major, and then you define system architecture. Now, we've been having this discussion as if it's only control systems engineer that works in building a plant. But in actual fact, there are so many other disciplines involved, right? The control systems engineer is one. The instrument engineer is another. Then we have the process engineer, right? Process engineers, most of them they have chemical engineering background. And they are the one that will be able to tell us that this crude must be maintained at X amount of pressure or temperature, right? And that how it must flow, the rate of flow, and whatever. So they will give you all of those parameters. So it is a team effort, right? So that is why. So the process flow diagram is just something like maybe drawing boxes. Okay, this is my wellhead. My wellhead will pass crude through a pipeline and then into a tank. And then this tank, I'm attaching a valve to it. And then a motor also. You know, that's what a PFD looks like. Maybe in subsequent lectures, I'll show you a typical PFD. Right. So you do all of that, and you have all these deliverables. You have your PFDs, your process flow diagrams. You have your control philosophy documents. You have your instrument index preliminary. You have your architecture diagrams. You have your preliminary cause and effect. Right? All of these documents help you to develop the proper control systems. Right? So once you are done with feed, you now go into what we call detailed design or detailed engineering. Detailed design, detailed engineering design, or detailed engineering, whatever it's called. But the bottom line is here is where you now develop your P and ID. Develop your P and ID, your detailed P and ID. In feed stage, you develop a P and ID too, but it is based on that high level information you have. It is during detailed design that you go into the details of every instrument. So that is when you define that this instrument must have a range of 0 to 500 psi, right? And this is where you go into details such that the wetted part, you can say that the wetted part for this instrument must be 306 stainless steel, right? You define the signal for this instrument. Oh, you define signal to be 4 to 20 milliamp. So all of those things, you now go into the fine details, and it's a lot of work, because if you have, so now look at this case study. Let's count the instruments here. You are okay. The instruments on the wallet is not even showing on this particular diagram, but let's count the one that is showing. You have 1, 2, 3, 4, 5, 6, 7, yeah, 8, 9, and even 10. So for all of these 10 instruments, you define their type, the specific type, you define their configuration, you define how they are going to be installed, right? You define the kind of signal they are going to carry. You define the weighted part. The weighted part is the part of the sensor that gets exposed to the process. And you not only define, you document, right? So each of these, you're going to generate what we call an IO list. Then you have your instrument index also. So it's a lot of work. I mean, for a mid-sized plant, probably of 10,000 IOs, you can easily spend 3 months on this detailed design. And that is even when you have proper manpower loading. You load proper manpower onto the project. So you develop that P&ID, you finalize your instrument data sheets. So for each of these instruments, you get their data sheets, right? And you will be talking to the supplier also to ensure that the instruments you are sizing is available, readily available in the market. Because if it is not available, let's assume that if you place order for this instrument now, the lead time for that order is 3 months, and the owner of the plant cannot give you that 3 months, then you need to size another instrument. And if you size this instrument, you need to evaluate its impact on this one, or its impact downstream, and its impact upstream. So those are the kind of detailed activities you do. That's why they call it detailed design. You go into all the fine details about it, right? So you develop your IO list. You develop your alarm philosophy. This is where you now do your detailed cause and effects. You have your control narratives, and then you do your network design. So you finalize the control narrative, and then you do your network design up to the hardware design and up to communications protocols. Even at this level, you define how your HMI screen will look like. And the deliverables you get is you have approved P&IDs, your instrument data sheets, your IO schedule, your control narratives, your C&E matrices, and your HMI philosophy. And this is the phase that determines 80% of commissioning success. If you make a mistake in this phase, your projects will be on a long thing, because rework are very costly, especially when the project is big and complex. Recall I said that if you have to change this transmitter, just imagine it. Okay. if you have to change this transmitter, for example, for you to change it, you need to evaluate its impact on this block valve. And you need to evaluate its impact on the instrument upstream it. Right? Now, look at a situation where you have done your procurement and everything, and you are doing your installation, and you now need to alter something. Let's even say that it's the impact is not much. Look at the time it takes you. We don't manufacture these things in country, or I mean, even wherever. Sometimes the manufacturer don't even keep it on their shelf. When you order, they produce. Right? So that is why the kind of work you do in detail design is very intense, right? And it goes through multiple iterations, multiple checks, multiple back and forth between you and the owners of the assets before you now arrive at, okay, so there should be another document here called AFC, and approved. So that is actually the final set of documents that you get, AFC. So this deliverables here equals to AFC actually. AFC is approved for construction. I mean, before you arrive at this approval for construction, you will have created some of these documents that you are just purely issuing for comments. Right? You are just issuing it for comment. So you can generate as much as probably 4 or 5. You can do 4 or 5 iterations, if not more. And that's even when your team is very efficient. Right. So someone said I should explain the deliverables again. P&IDs, piping and instruments. Okay, thank you, Colin, sir. P&IDs, piping and instrument drawings, right? So the P&IDs are the drawings that tells you, that represents, so what you are seeing on the screen, this image you are seeing on the screen is essentially a P&ID, right? But it is not, these are the essential things you see on the P&ID, right? You see the instrument and its name, PT101, that's pressure transmitter 101, FV102, flow valve 102, right? You can see the interlock and the ESD logic trip represented. This is a low level alarm. This is high level alarm. This is PT106. The output from this tank goes to flare, right? So that's what P&ID is. And then you can see on the P&ID, you see some, look at this line, for example, short dashes. It has what it means, right? It's a signal line. Look at this one. This is a pipeline, right? It's a physical pipeline. So that's why they call it piping and instrument drawing. Then the instrument data sheets essentially list the characteristics of each instrument. So you need to have a folder where all the data sheet of every instrument on your P&ID is. It tells you the model, the manufacturer, the model, the range, the calibration, the resolution, everything and even the mechanical construction, the connection interface to the process and everything. It tells you all of that, right? So you have that instrument data sheet, the I/O schedule. So that is I/O is input and output schedule. That is what defines what constitutes input. This PT, for example, constitutes an input, right? So that input will need to go into some kind of control system. So let's say it's going to some kind of input card, whether analog input or digital inputs, right? Or even if it is pulse, right? And then you have your control narratives that it's a document that explains in detail how you are carrying out the control. You know, engineer speaks in documents. So if I get to a plant now and you want me to look at something, one of the first thing I'll ask for is, can you share the P and ID for this plant? If I see the P and ID and I cannot determine the information I want, and then I can ask you, do you have the, I can ask you to give me the cause and effect matrix and the control narratives. Between those three documents, I will have a complete understanding of how the plant functions, right? So the cause and effect matrix essentially lists all the instruments, right? And let's say if instrument one fails, what are the effects on the process? So if, for example, we have a level, I hope you can see what I'm writing.
Yes, you can.
Okay,
Yes,
great.
we can.
Okay, thank you. So this level now, let's assume if the level in this tank fails, what are the effects? The effect is that there will be a spill of fluid from this tank. If we have a PT, a pressure transmitter, and that PT fails, it means that there is a possibility that the pressure in this tank will get elevated to the extent of rupturing, right? So we look at the cause, we look at the effect, and then it helps us to determine the mitigation, right? So if this level fails now, then something must tell the operator that this level has failed, right? If this PT fails, then something must tell the operator that the PT has failed. And then there must be a defined line of action to follow. Do you understand? Okay. So the key insight, this phase determines 80% of commissioning success. If you get it right, if you get it wrong in this detailed design phase, you're on a long thing, essentially. So implementation, once you have done your detailed design and you've done everything right, then you move into implementation stage. That is where you do your building and configuring the system, or we call it construction, right? In the implementation stage, there are basic processes underneath. Of course, before you implement, you have to do your procurement. So your procurement professionals will be involved. Immediately you finish your detailed design, you freeze your BOM, right? You hand it over to your procurement people. They do all the sourcing, and then they do the procurement. They do all the your financial controllers and all of those people. They do their job, and then the the expediters and the logistics people, they ensure that the materials come to you in your plant, right? And then you begin the construction, right? So looking at the image, so you create your HMI screen, right? You know, everything from your drawing. You can see your PNID and all of those things. You construct, you build your panels, right? Your network switches and all the hardware. You do your wiring, right? You write your programs, you do your configuration and everything, right? So you get all of that done, and then you move into a stage called FAT. You do your factory acceptance test. Essentially, you do the factory acceptance test will test against all the documents you generate. I mean, part of the documents you generated in detailed design is your FAT checklist, right? Before you even do your construction, you generated documents you have to get, to validate, right? So do your FAT, and then you ship the items to the customer site, right? Depending on the requirements of the project, the project might mean that you should do what we call an SAT, site acceptance test. That is, the equipment are already on the customer site, and then you need to do a test there. So from FAT, you move to SAT. All of these are under the building and configuring of the system, right? And then once all of that checks out, you move into commissioning, right? Then commissioning, so like I mentioned earlier, if it's a brownfield, you do your pre-commissioning, right? And if it is a greenfield, you do your if it's a brownfield, you do your recommissioning, right? And if it's a greenfield, you do your commissioning, right? Pre-commissioning is also a sub-process in commissioning, right? It's just like an interface between your construction and your commissioning, right? In pre-commissioning, you do calibration of all your instruments and all of those things, right? And then when you get into the commissioning activities, also, before these commissioning activities, during the detailed design, you have developed documents that you are going to use for commissioning. And even part of the detailed design is the training requirements for the operators and maintenance people that will run the plant. So you can see the detailed design is a massive, massive activity, and it is very, very critical, right? So you do this commissioning, and it follows these steps. You do your signals, and logic commissioning. So you test all your signals, your 4 to 20 milliamp, your 1 to 5 VDC, your logic, all your and or not, and so on and so forth. You do all of those. That is called commissioning. Hot commissioning with a live process, right? And then you do your control loop tuning. Tuning involves the responses of the valve, all the timing required, the response of motors and pumps, and so on and so forth. And then you do what you call an operator walkthrough. So you begin to involve the operators, right? And then you have your commissioning reports, you have your updated control logic, you verify your alarm limits, right? And your commissioning validates design assumptions against the reality. So it is at commissioning that you begin to see the results of your detailed design. But again, in as much as the detailed design is very important, right? The feed stage, feeds information into the detailed design, right? So if you get it wrong at the feed stage, it will make your work during the detailed design more complex. because you will need to do a lot more analysis, right, and engineering, you know. Okay, our time is running really quick. So RFSU ready for startup, and the criteria: all safety functions are tested, all alarms are active, all operating procedures are approved, all operators are trained, right? And the formal outcome is that the management sign off for live production, right? So you've introduced your process, whatever, and the management agrees that, okay, you have delivered what you're supposed to deliver, right? So at the RFSU stage, there might still be some punch list, what we call punch list. There must still be some punch list items, that is, some requirements that has not been fully implemented. But we can say that, okay, these requirements are not showstoppers, right? Without these requirements, we can still operate the plant safely, right? We still have very good insight into the process plant, right? And then we can still move to RFSU while we create a plan to clear out the punch list. And then after RFSU, of course, you hand over to the operations, right? So you have your as-built drawings. So you create another set of drawings that documents the reality. So that's what we call the as-built drawings. You have your control narratives. You have your alarm lists and all the settings. You have your operator manuals, the maintenance strategy, and the training records. So the final objective is to have a safe, stable, and operable production. So you can see how the project evolved from conception, from something that exists in your head down to a process. Okay, let me charge this. You know, from a concept in your head down to an actual operable production system. So going from that conception to feed to detailed design to implementation to commissioning to RFSU and then to handover, right? So that's what I mean. That is the context that I wanted to set for the year, right? You know, we've only spoken about, we've only discussed process, you know, how things evolve. And I decided on this path because I've spoken to many people that feels automation is just limited to writing programs and all of those things. For the young engineers, entry level engineers, and even students, I'm still going to have a discussion on the potential areas of specialization you can begin to look at, right? There are people, there are professionals on projects like this that we call them design engineers. All their job, right? All their job sits in this place. They do design, right? They do design. I mean, people that doesn't like the rigors of the field, right? You know, sweating in the sun, standing, wearing coverall, wearing ADAT, and all of those things. Their job is computer. Their main tools are computer softwares and then their knowledge, standards, reference materials, and all of those things. And it's a specialty. And we have a lot of design engineers in Nigeria. And then we have field engineers. They go to the field, and then spanners and bolts, screwdrivers, multimeters, and that is their job. There are another set of guys that are just commissioning engineers. That is their specialty. Just give me the drawing, and then you have finished your construction, then I come in, and then I start the commissioning, right? So they do commissioning up to RFSU, right? And under detailed design, you have different people. You have instrument designer, right? The people that looks at the instrument, the size. Instrument sizing is not a small job. It's a very intellectually tasking job, right? There are control systems engineer, people that will select the control strategies, do all the calculations, model the flow, model the logic, and all of those things, right? And then we have the programmers, people that will write the code. So you can see that there are different areas of specialty in this project evolution. So that is what we have set out to do today, and I think we've achieved that. So going forward, so this opening session is not about teaching everything at once. It's about framing the journey. So our subsequent tutorials will deep dive into control theory and tuning, right? The PID, of course, cascade, where and when we use cascade controls, ratio control, feed forward, even advanced controls. Do we really even need them? Statistical process controls, and all of those things. How do we take those things out of the paper and relate them to exactly what is happening in the plant, right? I mean, for some of us engineers, we're just excited about the machine, making things work, building things and whatever. But when you get into the business environment, nobody cares about your high-tech equipment. What they care about is, can this equipment save me money, or can it make me money? If it cannot do any of those, then it's a toy. It's essentially a toy. You can just go home and be playing with it, right? So we'll look at all of those control theory and tuning. Tuning is very important in a plant, right? I mean, it's just like your vehicle. If you don't tune it, it consumes a lot of fuel, thereby impacting your pocket. But if you tune it very well, the fuel efficiency goes up. The same thing for plants. If you tune, excuse me, if you tune your plant, your control system properly, right, it saves energy, it drives efficiency, it reduces waste, So we'll look at PLC and DCS programming. We'll look at control system components. Beyond PLCs, we have other components, the VFDs, the motion equipment, the all the different sensors, switches, and all of those things. Then we'll look at industrial networks and protocols, right? I mean, there's no way we'll talk about industrial networks and protocols that will not stray into cybersecurity. We'll look at safety systems. How do we protect our machines and processes? We'll look at alarms and human factors, testing and troubleshooting. So the goal is that every deep dive will connect back So the life cycle we introduce here. The simple goal or vision for our engagements this year is to connect the abstract aspects of automation and control system with practical realities. Because I've been there before. You get into the plants and you're talking. I used to work for Rockwell Automation, and you get into the plant and you're talking about the fantastic features of the PLC. It can do this, it can make you to do this and that and that. And you see all of these people with their hands on their chin, just looking at you, talking and talking and talking. And at the end of your presentation, nobody will ask any question about a feature. They will just tell you that, okay, how much is this thing? You say, okay, it's $X,000. If I put in $X,000, if I make this investment, what do I get? And you're like, come on, you see all this fantastic, the Logix AI feature, of this card and all, but they don't care about all of those, right? So we need to make that connection so that you as an engineer or as a technician, you will be able, to connect the technical and the technology with business realities, with economic realities. And you'll be able to have that discussion, and it makes your life so much more easier. So all of these are online engagements, right? But there are other. So if you want to, beyond what we can teach here, right? There are paid trainings. In fact, there is a paid training presently going on, where we're using this same case study, and we started from the conception, we did the feed, did some detailed engineering, and then we are writing the program, right? So we write the program and we do all the simulations and everything. So there is paid training for a very deep dive into all of this, but the bi-monthly, I hope that we'll be able to stick to that. We'll be as quality as can be, and we'll not let back on knowledge. So thank you everyone for your time and your attention. So we can take questions now. We have about 18 minutes to take questions. Thank you. Okay, Collins. I think Collins. Okay. Thank you. Will you be able to? I don't understand that first. So maybe you reframe it, Collins. Then, so who raised hand first? I can't hear you.
Can I say something, please?
Yes, go on. Yes, go on.
Okay. First of all, thank you so much. Thank you so much for the program. We really appreciate. Honestly, you really did much this morning. We thank God for that. Okay, my question is, I just have two questions. The first question is, can one person be a design engineer, field engineer, and then a commission engineer at the same time? Is it possible? And the
Well,
second question
not at the
is,
same time. Okay.
okay, sorry. The second question is, you made mention on the paid training. How do we assess such training, please? Thank you.
Okay. So for the first question, an engineer, so oftentimes oftentimes you start, an engineer you can function as a commissioning engineer or a design engineer or a construction engineer, right? But you can't do it at the same time. But then for the money, because of managing manpower, because detailed design precedes commissioning. So we can move some engineers from detailed design stage into construction. We can also move them into commissioning, based on so you can, in terms of skills, you can have the skills to do all of those. So my specialty is control systems, right? Control strategies and so on and so on. So I function within the controller space. But I started off as an instrument engineer, so I can do instrument design. Right? I can do instrument design, but I now prefer just to stay so that I can sit down in the control room, do my work on computers, and then sip coffee on the side, as opposed to being in the sun and sweating. You understand what I mean, right? So you can function across board. Okay. Yeah. Funke, your question, you can unmute and ask.
Okay, good morning, everyone. First, thank you very much, sir, Engineer Dapo. We appreciate your time. Seriously, I'm in the field. I'm in automation engineer, but I love attending your class because they give you a structured learning to what automation is about. And for what you've said today, I've learned a lot. And also, as an engineer wanting to dive into this field, just for the engineer in the aspiring automation engineer in this room, being an automation engineer is a wide thing, is very, very wide. You need to understand what the process engineer is talking about, what the mechanical engineer is talking about, what the operator is talking about. You need to know your ones and zero. Please, if you want to come into in this industry, and like what you said, our lecturer in school did not do a good job. I always remember some like doing my control system engineering course in school. You just be hearing calculate your tau, calculate your time delay. How do you convert digital to analog signal? Guys, you will need those things when you are here. You will need them. Those calculate millivolts, micro, you will need them. If you really mean business and you want to join this field, it's very interesting. And one thing I like about it is that you don't get bored if you're an automation engineer because every problem is a different strategy, how you solve it. My advice just like pick your control books, read it. And when you are reading it, there are some textbooks that they call industrial, like what is it called? Like a textbook is not like about calculation, but it tells you what industry entails. Please read it. The industry is so nice. And I like what the automation experts in Nigeria are doing now. They are encouraging youth to come into automation. Okay, my question is, please, what is our next topic? If you already have that in mind, so that I'll be racking my head and read ahead so that I write the necessary questions. Thank you very much, sir. I appreciate your time and efforts and resources in organizing this class.
Yeah, thank you, Funke. Funke is one of my organs in one of the big organizations around. Thanks for your time in joining, and thanks for the comments. I will announce the. I'm trying to just create a series of programs, a series, so that we'll have like a table. I'll just drop it on the WhatsApp group. If you're not on the WhatsApp group, it's best you join so that we can. I mean, that's the primary place where we pass across the information. So both information for the paid training and the tutorials will be dropped on the WhatsApp group. So you will see the the topics we have plans for, and I'll be asking for volunteers to support in organizing this free training. It takes a lot in. So this is my first time using Canva for presentation. I had to sit down and learn and learn. Old school PowerPoint. But Canva seems colorful and whatever. So I'll be asking for volunteers to help plan, proofread, and so that we can all contribute to the community. Right. Mazook.
Good morning, sir.
Good morning.
My name is Ayode Marzuk. I have two questions. So the first question is, in one of the earlier slides, you mentioned that the pipeline can be submerged underwater. So you also mentioned all the effects of how the pipeline can corrode and all the harmful effects that the pipeline can have. So I want to ask, what actually informs the decision to place the pipeline underwater when we know that it could rupture, it could corrode? That's my first question. My second question is, you mentioned that we will be submitting an as-built drawing as one of the deliverables, I think. So I want to understand how it is different from the P&ID, because with regards to mechanical and electrical drawings where you have dimensions, you have this line, 50 meters, or different things. I don't know if that is included in P&ID. So I also don't know how changes would occur during the implementation. So thank you.
Okay. Yeah. So for the first one, oil, for example, you can find it anywhere. You can find it in the land. You can find it in swamp. You can find it in the sea. So in Nigeria, for example, I don't have any estimate, but we have, I think, thousands of oil wells right in the middle of the Atlantic Ocean. Right. When you see countries fighting about water, the right to water or whatever, what they are really fighting for is the mineral underneath it. So if the oil well is located on the Atlantic Ocean, then the pipeline most of the time will be subsea pipeline that will take the crude to land one way or the other. So that's the answer to that. For the second question, as built, so when you have done your design engineering, right, engineering, and you produced your P&ID and other documents, during installation and construction, some things you make some, we are not perfect. So we make some modifications here and there. And once we make that modification, we need to document it. So after installation, we now update the drawings we created during design engineering, and that become as built, so that people that wants to maintain and troubleshoot down the line will have the correct information about the plants. Yeah. Okay. Salome.
Good morning, sir. Thank you for the tutorial. So my question is, let's say you're supervising a project from the beginning to the completion stage. How do you assign the weights of the percentage of completion, or the percentage of each section? What percentage weight is installation? What percentage weight is the design? And even within the design, how do you assign the weight of each section of within the design? I don't know if you get my question, sir.
Yeah, I do. Because of your reporting, every day you need to say, okay, this is percent complete and so on and so forth. So there is no scientific, or let me say absolute way for you to determine it. So it's an estimate most of the time. It's an estimate. And of course, for a project like this now, the detailed and engineering design often carry either the detailed engineering design or the construction. Between the detailed and construction, they carry more weight. So you estimate. So let's say if you have you can estimate in time. So for example, now you have a project, you need to do it in 1 year, right? And then in your project management, in your project planning, you've assigned the feed to be, let's say, 2 weeks, right? Your detailed design, you assign it to be 3 months. Your construction, you assign it to be 4 months. Your pre-commissioning 1 month, commissioning 1 month, and then RFSU 1 month, right? So you can use that now to now scale it based on that percentage. And then your detailed design, that is 3 months. So all the activity, because all of those activities in that detailed design, you will create what we call a WBS, right? When you're planning the project, each single task will be identified and it will have an identity. So it's a subjective thing. There is no hard and fast rule for you to assign the weights. It's bottom line is it's an estimate that you just put together. Oftentimes, for example, oftentimes in the field, we even so if I know that a job is 70 to 80% complete, I try to be conservative and give it like 50% because I don't know the kind of problem I'm going to encounter in the future, in the evolution of the problem. That maybe if I had planned 1 week for that activity, it now takes me 3 weeks. So I try to be conservative so that I don't want to tell my management that, look, I'm stuck in this place for forever. Whether it's dishonest or whatever, I mean, it's the practice we do see in the deployment of a project. So I cannot tell you in plain terms how you do it, but it's an estimate. But we can discuss your specific situation. You can buzz me, Salome.
Okay, thank you, sir.
You're welcome. Yeah. So David next. David Uluwadare. Yeah.
All right. Good morning, everyone. Thank you so much, Engineer Dapo, for giving us this wonderful presentation and lecture. And just to add up, I have been in a project whereby I started off from the design, construction, pre-commissioning, commissioning, RFSU, and all of those things. And then I can agree with you that it's a whole lot of effort and time and many things, all manner of things included, right? And then the last person asked about trying to the time range or something like that. And then you said 50%, like you're going to be giving 50% before all of those things. And then I will agree with you because there is a time whereby we are done with construction. Now we are in pre-commissioning. Then from pre-commissioning to commissioning, it took about like 1 year, 6 months. All right.
1 year, 6 months.
Yes, because from when we start introducing the gas, they will say, oh, they need to cut this place. Oh, they need to shift this one. Oh, the pipe now is now bigger than what we thought. Reduce it again. Change this valve. Change this controller. You understand? So
Yeah.
you cannot say that we are already 90% and now say you are going back to 50%.
Exactly.
So that's why it's very good to say, okay, 50%. Then when you say that, okay, it's already getting to completion at your own taste, to complete everything, you can now say, okay, maybe 60, 70, so that you don't go and shoot yourself in the leg. Right?
Exactly.
So thank you so much for all of this information you reached out. I can resonate with you because I've been into the process too. Thank you so much.
Fantastic. Fantastic. Thank you, David. So, okay, David Toby. Is David Toby still there?
Yeah, good morning, Engineer Dapo.
Yeah, good morning. Your voice is low.
Okay. Good morning.
Yeah, good morning.
Yeah, my question has been answered. Thank you very much.
Oh, okay. Fantastic. Thank you.
Yeah.
Olalekon, you next.
Good morning. Can you hear me?
Yes.
Okay.
Please, I want to ask a question. Okay, I will use an instance to make it more clearer. Assuming maybe I'm trying to award a panel bid to, okay, Greenpeace, for instance, and most times they might have done the kind of project and they have the templates they use. And from the design given to me, their own design, they use maybe Siemens for some component there. And later, at the end of the day, ask why celebrating with my in-house engineering team, they prefer using ABB, which is against the template of design they are used to or they already have for that kind of project. For that kind of situation, how do you try to convince the clients, or how do you manage that kind of situation? Because at the end of the day, it might make you go back to drawing board again in terms of designing afresh or something like that. That's the first question. Secondly, I've seen sometimes, or I've read about some project that they said it fails at the engineering stage. I mean, at the front end stage. Those kind of situations, are they always attributed to maybe the budget of the client, or maybe the technical complexity involved, or maybe other factors? Thank you.
Okay. All right. So for the first question, the selection of components, design methodology, and all of those things, it's not purely tied to technical. There is a business aspect to it. So if you throw out a bid and you say, hey, build this panel for me, company A, B, C, D sends you a proposal. They have sent you a proposal. In their proposal, they are going to try to meet your quality requirements. They are going to try to meet your cost requirements. And at the same time, they are going to try to meet their own profitability targets. So if, as a company, I have a template and I have some materials in stock that I can use, which means that if you give me the project, I can promise that maybe these other companies will have to go to Europe or the US to buy materials. But since I have it in my store, right, I can promise you I can deliver this project in 1 month. Others will be promising 3 months. So that is my number one competitive advantage. Secondly, since I have a template of the design, I can quickly do an adjustment, pam, 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 and then speedily, produce your panel. I have the template. I have built that type of panels before, meaning that I have experience in it. It assures you of quality, speed, and response time. So those are the competitive advantage they brought to the table, right? And that is what they are selling. So if you now come and say, oh, you sized Siemens for this, okay, I don't want to mention names, companies are sensitive to these things. So you size controller A or breaker A for this, but I prefer breaker B. The first thing we need to know is that all these major organizations, all their products are quality because all of them conform to the same international standard. The configuration might be different, but the quality is actually undeniable. From Siemens to ABB to Rockwell to Danfoss to all of these major global organizations. So we need to agree on that. So you might be requesting for component B simply because your personnel, your in-house personnel, are trained and experienced on component B. But your service provider have templates and whatever for component A, right? And your service provider has issued you a quotation based on component A, right? So if you say component B, then there will be a cost change implication. There might be a lead time implication. So it will now be that two of you need to sit down and negotiate. maybe if you are willing to assign more money to the project, your service provider can bend to your will. Or if you don't want to assign money, can you ask the service provider, okay, as part of this, you have to train my people because they are experienced in component B. So if you are bringing component A, then provide training for my people. So it's that trade-off that you need to do, and then you get your project done, right? The second question, okay, so I've forgotten the second question. Can you quickly remind me?
Like some projects, they fail at the engineering design stage. What caused that most of the times? Is it maybe the budget or some other factors like maybe political factors or technical factors?
Yeah, so I mean, so many things. So when you do your conception, one of the processes I skipped was feasibility studies. So you do a feasibility study. For example, if I want to build a gas plant somewhere in Niger Delta, right? And I do my feasibility study, economics checked out, technical checked out, political environment checked out, government policies checked out, foreign investors checked out, everything checked okay. And feasibility studies happen at the very beginning, immediately after your concept, after you conceive the project. And then during detailed engineering, you now have maybe youth restiveness in the environment you are supposed to do your project. And you analyze the situation. The root cause of this restiveness might not disappear in another 2 or 3 years, right? You don't want to go and procure materials and just keep it in the store, hoping that restiveness will go. That means that you are just keeping money in the bank for 3 years. Money in materials in the warehouse for 3 years. Or within the time you did your feasibility study and the time you want to execute, government policy changes. Let's say the government changes from one government to the other, and the other government says that, okay, all gas processing facilities in this country are hereby nationalized. That it becomes government owned. Who can battle with the Lord? You just have to step back and say that, okay, I don't want to build a gas plant that will donate to the government. So, so you just step back and just stop. So technically, the project failed at that point. So there are so many reasons for a project to fail. Look at all these big. Look at the Olokola LNG, for example. It took many years before government arrived at what they call the FID, final investment decision. So it's just a whole lot of dynamics. Even again, look at what's happening in global politics. You have an aggressive policy to drill for oil, to explore and produce oil. But your main buyers, let's say America now have access to Venezuelan oil, I mean, in quotes. Let's say China also, those are the two main guzzlers of energy globally, right? And Europe. And then they found other buyers. So you now ask yourself, if I produce this field, whom would I sell it to? So it can cause you to decide to say, okay, let me just relax on this and then watch how things progress. So, I mean, different things can happen to make a project fail at any stage. Ali Soliu, you next.
Okay, yeah, great. Can you hear me, sir?
Yes.
Okay, thank you for the insightful session. and I appreciate it well enough, sir. Yeah, so I will say that I just need your it's not a question, it's a question, but let me say a guidance from the guidance perspective. I had my BSc in mechatronics engineering, and I'm actually doing systems and control engineering in my postgraduate studies now. So, however, which I know that I would definitely love to go back to the industry. Though the major industry experience I have is in the software aspect actually, but if I'm
Is it
actually
what?
going back to the like as a software engineer, that's the industry
Okay.
experience I have. Yeah. So, but I would definitely after my postgraduate studies, I'll definitely go back or love to go to oil and gas sector as a control and systems engineer. However, definitely I know that it's not possible to be do it's actually possible in one way to actually enter the industrial and gas industry. But what I know generally is that what people care in the industry is that what do you have on your head, what can you do, what can you deliver. So I've actually have it in my brain that one way or the other, any summer holiday or something that is open for me, I would love to get my hands-on experience. Is there any guidance you can give regarding the path that I can take to actually have this gain this hands-on experience before getting done with my postgrad studies and let me say try to enter the oil and gas studies after that?
Okay. I mean, the first thing I'm going to say is, even as of today, there is still a scarcity of qualified personnel in the industry. And even if your preference is oil and gas, in the automation industry, which involves oil and gas, manufacturing, food and bev, mining and cement, and all of those things, even the mining industry in Nigeria is coming up, so there is space. The question is, how can you position yourself to take advantage of the employment opportunities, right? It's a chicken and egg thing. For you to get experience, you need to be on the job. For you to be on the job, you need to have experience. So the middle ground for now is for you to be able to demonstrate at least some skills that can warrant someone to take a bet on you that, okay, I think you have the potential to do well in this field. And how do you do that demonstration? You need to have, what's it called? You need to, so often it's even easy now with the internet. You need to create a portfolio, right? You need to create a portfolio. And one of the things I advise most is, if you're searching for opportunities, LinkedIn is one of your first efficient and the cheapest avenue. You need to be present on LinkedIn, right? Follow people in the field you are targeting, right? And then begin to develop. Even if it is all you can do for now is theoretical. And that is one of the reasons for this forum, right? Even if it is theoretical, begin to develop it. Join professional association, right? There is the ISA, and there are other bodies providing this kind of support for the industry. There is the automation circle, right? I think they also have a tutorial. I can't remember the date. There is the I think Niger Fest. They also have an upcoming tutorial, right? You cannot overlearn, right? And then as you are present in events like that, you network with people, right? And then you get exposed to more opportunities. In simple terms, define the area of entry, your entry point into the oil and gas industry. At a minimum, understand oil and gas process. even if you don't know how to control it, how is oil, or how do they find oil and gas? How is it extracted? How is it processed? What is the value chain from exploration up to the downstream? What we call upstream up to the downstream. What are the stops in between? Have that understanding. Since your interest is control system, where does control system play in this? I would drop a document. It's a book by one of the major OEMs. I will drop it in the WhatsApp group. And it's quite a long book, but it can act as a reference book for you to understand how the oil industry works and all the functionalities, all the professions, no, sorry, all the specialties rather, that makes things happen in the industry. So I will drop that.
Yeah. Thank you so much. I'm very grateful. Thank you, sir.
Okay. All right. Thanks, everyone. I think we've overshoot our time by 14 minutes, of approximately 15 minutes. Thank you for your patience. If I may ask, if little favor, you can just go back to the LinkedIn, whatever, and just put your comments, your impression, and whatever on the post. I'll make a follow-up post on this later in the week, and then in 2 weeks' time we will reconvene. But pending that time, I will drop some information in the WhatsApp group, and then we'll take it from there. Thank you very much, and have a beautiful weekend.
Sorry, can you drop the link to the LinkedIn group, please? Yeah, we can drop our comments.
Okay. All right. Can you please drop that? Can you please drop that link on the LinkedIn post? All right, are you there?
Yes, sir. I'll drop it now.
Okay, so just drop it in the comments.
Okay. So I really appreciate it. Thank you so much. God bless you, sir.
Thanks to God. All right, guys. Have a great week. Okay, no, weekend first. Let's enjoy the weekend before the week comes in.
Okay, you've seen that. Thank you.
Yeah. All right.